Hello, statistics student. This video is for chapter 10.1 and 4. We're still doing a hypothesis test for two population mean. In the first two example, we did summary sample with X bars and so X bar and S1. So they are independent samples. You don't even know the data value, so there's no way to pair them up. So starting from example 3, we are working on some more different types of samples. So example 3 is still an independent sample. So look at this. So we want to compare seatbelt use to see if seatbelt use actually make injury for children less severe. So that's what they say. The study of seatbelt use involved children who were hospitalized after car accidents. For 123 children who are wearing seatbelts, the number of days in ICU has a mean of 0.83 days and a standard deviation of 1.77 days. So these are wearing seatbelt, and then the sample of 290 children who were not wearing seatbelt. So they are two different samples, different sample size, so not pair up. Okay, they're independent, and they also have their own sample size, their own mean, their own standard deviation. So because they're written in a paragraph, we copy them down and define the two populations. So in the question, they talk about people that children that use seatbelt first, so that would be population 1. So we want to do a hypothesis test that seatbelt use is effective in lowering degree of injuries. So see how they don't tell you about greater or less than. They kind of use the word lower, but is it really less than? Now, if population 1 is people that use seatbelt, population 2 are those that do not use seatbelt, then we should have meal 1 should be less than meal 2. You really should use lower, because that would mean seatbelt is effective in lowering, right? You should have a lower hospital stay, ICU stay than the second group. Okay. So this is how we define the claim. So defining the claim is most important. Look at the claim in more detail. So if it is effective, that means meal 1 should be lower than meal 2, because meal 1 are the one defined as wearing seatbelt. So that's how you analyze it. And then you collect all the data, and now you're going to enter it into this analysis hypothesis testing, mean two independent samples. So I will have, what is the claim? The claim is less than, right? It's a left tail test, less than 123.83, 1.77, 290, 1.39 days, and 3.06. 0.05 for significant level. And so these are pretty standard. The most important one is to define which one is the one that you seatbelt. Again, I just want to emphasize this. If you mix them up, then your claim has to match. Okay, and usually we actually want to define those that are mentioned first as meal 1. Okay, so the null hypothesis should be equal. The alternative hypothesis would contain the claim. So you have to take a note that this is the claim. When we do conclusion, we have to use it. Okay, so we're going to do the hypothesis test for this analysis, hypothesis testing, mean two independent sample. We have statistics, and it is lower than, right? Less than 0.05. So the first is 123, 0.83. Standard deviation is 1.77. They did not give us this, so we just give it 290, so that they will use t distribution. If you don't have standard deviation, population standard deviation 3.06. So 1.39, 3.06, 290, 123.83, 1.77. And by default, we do unequal variance t distribution. So the t test statistics is negative 2.33. P-value is 0.0102. And the confidence interval is negative 0.96, mu1 to minus mu2, negative 0.16. So both of them are negative. So you can see, and it's 90%. 90%. They create this for you. So let's go back to the notes to say, see, I run it this before, so it's negative 2.33 period upon this. It's a 90% confidence interval. That's the output, right? Then what should I make my conclusion? 0.0102 is less than 0.05. So it is a surprise difference. So x1 bar, x2 bar, although there doesn't seem to be very different, it's 0.83 versus 1.39, but because of the size of the standard deviation, they are actually quite rare. The difference is quite rare. And we will reject x0. X0 say that they are the same. We rejected it. That means there is significant difference between the mean ICU times. So because it's a rare sample, we say there is sufficient evidence to support the claim. Why do I say I support the claim? Because the claim is in HA. If we rejected X0, HA will be supported. That seatbelt use is effective. You don't talk about mean or whatever, you just say that claim is effective in lowering. Now, you can also analyze the confidence interval as negative 0.96 and negative 0.16. See, both of them are negative. That means when you subtract these two mean, it's always negative. How can you have a negative number when you subtract two numbers? It must be mu1 is lower. Lower minus a higher number will have negative. So you can see that the seatbelt one would have a lower ICU time. So both the hypothesis test and confidence interval make the same conclusion, saying that seatbelt use is effective. The fourth example is switching to use data now. So we are looking at course evaluation of female professor and male professor. They're not paired up. It's one group of female professor, the other group of male professor. These are their evaluation score. And we want to test the claim that there is a difference in mean evaluation course. We say we want to test that they are different. Male and female professor had different evaluation score. So first is determine if they're dependent or independent. Of course, they're not dependent. There are two groups. You can also see that their sample size are different. Although we have data value, but does not guarantee that it is always paired up, right? The two groups of samples, some female professors evaluation grade, some male professors evaluation grade. So before we do anything, after we figure that they're independent, we have to define the two populations. So because female professor is being discussed first or given first, so we just define it as 1 and define male professor as 2. And because data is given, we enter the data to stat this. Then we are going to write the claim. The claim say what? There is a different mean evaluation score. That means mu1 is not the same as mu2. We don't care if it's greater or less than, they're just not the same. And then the null hypothesis in all cases is always equal. Mu1 is the same as mu2. There's no difference. And so in this case, the alternative hypothesis has to be not equal, and it becomes the claim. Okay, sometimes when people see, oh, there is a not the same, then they thought that the claim is in H0, but actually the claim is actually in H alternative, although it is not equal. So again, these are standard things. If it is not equal, it's a two-tailed test. And so we are ready to put it in. So because of data, I have already put the data. So I'm going to do it in here. Instead this, I copied it over here, female, male professor. And I'm ready to do hypothesis test, mean 2 independent samples. And because I have data, I use data. So previously, the first 3 example is always summary statistic, but now I use data. First, select the alternative hypothesis that they are not equal, right? Because that's the alternative. Write the significance And then you just tell them which one is sample 1 matched to population 1, that's female. And that is sample 2 is male. Those population standard deviation sigma 1, sigma 2, and use unequal reference. You can do the evaluate to find test statistics. T is negative 0.66, right? P-value is 0.5172, so it's quite big. And the 95% confidence interval is negative 0.528 or 53 and 0.27. So in the confidence interval, you have one negative, one positive. P-value is quite high. Degree of freedom is 19. Okay, so these are all output. You write down, typically we write down the test statistics. So your sample is below the mean by less than by 0.6 standard deviation. Your p-value is 51.72%. There is a high chance of getting it if there is no difference. So maybe there is actually no difference in the evaluation score. So and then you write down the confidence interval. Because p-value is greater than 0.05, it's not a rare sample. So we say we cannot reject 0 because x0 and the sample agree with each other. Conclude no significant difference. You can actually make the conclusion now. And then for the exact wording, because the claim is in HA, you say conclusion about the claim would be there's not sufficient evidence. Whenever you're not surprised that not sufficient evidence, and because x0, look carefully, x0, no, the alternative hypothesis here is the claim. So we use the wording supports, not sufficient evidence to support that there is a difference. We don't support there is a difference, meaning there is no difference. Okay. So we can also look at the confidence interval. If there is a difference, what is the difference? It turns out the difference could be as low as negative 0.53, as high as 0.27, but it contains 0, so meaning there could be just no difference. So we say there is no significant difference. The sample does not support that there is a difference. So that is how you do it with data. They are still independent. Now the next one is switch. It's actually 10.4 when we are dealing with data that is paired. So look at this. This is a data that's collect weights of students, 1, 2, 3, 4, 5, 5 students. Their September and April weights. So it is all matched because it's from weights from the same students. And we want to test the claim that again that there is no difference. No difference means the same. The last one we test that there is difference, that is not equal. No difference. We want to test that they're the same. That there is no weight gain for freshmen. You know, the freshman 15, the first year you gain 15 pounds. Well, I guess if we stay home for COVID-19, it's very easy to gain 10 pounds, right? So the samples are dependent because pairs of value are from the same students. And we define something called difference, which is the first minus the second. September minus April. Now, when I say enter the data to statistics, I do not mean enter D. I actually means enter this into one column and enter this into the second column. Statistics can calculate the difference for you behind the scenes, although they don't produce it for you. If you are to find it, you have to do it on your own. And then we say because there's no difference, our claim is mu of D. So we don't say mu1, mu2, we say mu D if we have dependent samples. Just this you need to remember. You introduce something called mu D, you run the statistics hypothesis mean match pairs. So I don't have that much time, so I would just run it really quickly. Hypothesis test mean match pairs because it's dependent. So you would say that the alternative is not equal. You want September and April evaluate. So that is the test statistics 1.23, p-value 0.25, and yeah, so that's p-value how